Polygonal meshes are the most common representation in modern computer graphics applications. However, due to their rigid structure, they're very hard to tune with gradient updates. They're as solid as a rock. On the other hand, recent differentiable rendering methods rely on implicit representations or point-based representations that are continuously differentiable with respect to their degrees of freedom. The goal is to retrieve the 3D space from a set of point views. For example, neural radiance fields, aka NURFs, achieve this by fitting the radiance signal using a good old MLP. Or 3D Gaussian splats that learns the structure of the scene by optimizing the positions and appearance of a sparse point set. Both techniques rely on volume rendering to learn the scene's underlying structure and appearance. Think of it this way. Volume rendering is a weighted sum of colors along the ray, where the likelihood of a ray terminating at a particular point is given by a probability distribution across the ray segments. As it turns out, volume rendering is actually related to volumetric mesh representation. In 2005, a report by Nilsson Max described a volumetric tracing algorithm on GPU through tetrahedral grids, integrating the radiance from one cell to the other. This observation raises a critical question. Can volumetric differentiable rendering finally be related to mesh-based representations? 5 years after NURF's debut, we finally find the answer. Today, I'm presenting Radiant Foam, a co-led project by Sherry Sudhan, Govindarajan, and Daniel Rebain. This novel differentiable representation is based on volumetric polyhedral meshes. Intuitively, you can think of it as a foam or a bubble that progressively learns the underlying structure of your scene. And this representation is injective, as each point in the 3D space corresponds to one particular cell. Changing mesh structure by altering the vertices' position or their connectivity represents a very difficult task for gradient optimization methods, because it can lead to overlapping regions. To address this, the mesh connectivity is defined by Delaunay triangulation. In Delaunay triangulation, the circumcircle of the triangles contain no other point from the sparse point set, making the connectivity an implicit function of the vertices' positions. While this setup is mostly differentiable, except for one particular case, known as edge flips, in that, while a point is continuously roaming in the 3D space, it can suddenly break the Delaunay constraints, causing a sudden shift in the volumetric field. This can lead to unstable training, as the position on the lost landscape would change very abruptly. As it turns out, Delaunay triangulation has a twin sibling that looks at 3D space from a different perspective. This is known as the Voronoi diagram. In this setting, the space is divided into convex cells, parameterized by a seed point at the center. And each point in the cell is closest to its seed point than to any other point on the diagram. The centers of the circles of the Delaunay triangles are none other than the vertices of the Voronoi diagram. And if an edge is drawn between 2 points on the Delaunay triangles, that would correspond to a shared boundary in the Voronoi diagram. While it might be intuitive to think that the Voronoi diagram would inherit the same discontinuities as the dual Delaunay representation, this is not the case actually. The discontinuities from the edge flips kind of hide behind the Voronoi diagram. They're effectively absorbed within the zero edge area, making the Voronoi diagrams a smoothly continuous differentiable representation for the 3D space. Finally, to render along those volumetric Voronoi diagrams, you simply cast a ray and you traverse along the neighboring cells, as the connectivity graph is encoded within the dual Delaunay representation. And just like classical NURF models, our fitting is supervised directly using the L2 photometric loss. And to eliminate the floater's artifact, the training is regularized by encouraging the volumetric distribution along the ray to collapse into a Dirac impulse. This ray tracing pipelines works very efficiently without the need for acceleration data structures. And it naturally supports light absorption effects like reflection, refraction, or even nonlinear camera models. And without the need to change the underlying scene representation. All you need to do is to tweak the way your rays are being cast into the scene. And unlike point-based representation, the non-overlapping nature of the polyhedral meshes avoid popping effects, which can be very distracting in the VR setting. The benchmarks show up to 200 frames per second rendering speed, which is very competitive to the state-of-art Gaussian splats model, and also a very competitive piece in art to the basic implementation of 3D Gaussian splats. However, because this representation is very novel, all the follow-ups from the NURF papers or the Gaussian splats papers must propagate, which leaves plenty of space for exploration. For example, how do we reconstruct dynamic scenes? And how about fuzzy surfaces? What about cementing understanding? Inverting physics and relighting the scene would be also a very cool area of exploration. Thank you for watching.